welcome back. Sorry for that. I just hit my desk with my chair. But anyways, going back to picking up rather where we left off. We have to look at current electricity now. Current, electricity, CITY. And the basic definition for current electricity is electric charge in motion. Okay, electric charge. Please note, I never said negative charge, I never said positive. I said charge. Because current can be made up of both positive and negative charge carriers. For example, in a metallic conductor, you have primarily electrons. In a semiconductor, you have both positive and we have both, yes, both positive and negative charges. And in an electrolyte, you have the movement of ions, anode, cathode, cations, and ions. So an electric current or current electricity is the flow of electric charge or electric charge in motion. Easiest way to describe it. There are two types of current electricity. We will look at the simplest type first. Direct current or direct, direct, current. We call this D dot C dot DC. Now, DC is simple. It's uncomplicated. It is easy to remember. You see, direct current is current whose value does not change over time. One thing, all the time. The value is fixed over time. So, this comes from, we get this from batteries. We get this from rectifiers, TIFIERS. This is direct current. Very simple, nothing complicated. The complicated one is alternating current, which we will now look at. Dun 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 dun. ALTERNATING, current, or A dot C dot AC, as the name suggests. Alternates, changes, varies. It is your typical sine wave. I'm sorry for not being able to draw a perfectly smooth wave. So AC, that's value changes over time. We get AC we get this from generators. We get it from inverters. Inverters convert DC to AC. Rectifiers convert AC to DC. We will have to look at rectification a smidgen a bit later. Now, where was I? Yes. So, I lost my train of thought. Yeah. Since this is an alternating periodic waveform, it has a frequency. Frequency is equal to 1 upon the period. And the definition is similar to that, the definition we had when we were looking at waves. This is the frequency, QUENCY, in hertz. and this represents the number of complete wavelengths or oscillations or cycles per second, and this is period in seconds, and this is the time taken for a complete wavelength or oscillation or cycle. So DC and AC. Have I missed anything? Have I missed anything? I can't remember off the top of my head if I have or have not. But it is time for us to define a few terms, since we're looking at current electricity. By definition, current is the electric current, that is defined as the rate of flow of charge. What charge are we talking about? Electric charge, either positive or negative. This gives us a formula. The formula is I is equal to Q upon T. Q is the unit of electric charge. The unit of electric charge is the coulomb, COULOMB, and it is represented by capital C. Charge is measured in coulombs. This is electric current, and this is measured in amperes, named after a dead dude. So is the coulomb, by the way, AMPERE, capital A. Common T is time, measured in seconds. Now, whoa, my voice went a bit funny there. Current flows because of voltage. I know. You see, you need a voltage in order to have a current. But we define voltage as the work done moving unit charge. Unit charge, CHARGE. Work done per unit charge. This gives us another formula. V is equal to E, or in some cases W, over Q. Depending on where you look, you might see W. Voltage measured in volts, charge measured in coulombs, capital C, and work measured in joules, JO. I put the unit without the quantity, work. Either the work done or energy used up in joules. Yeah, joules. And these be a few interesting definitions. So, current, voltage, and one other quantity are very, very, very closely related. This quantity is resistance. 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 Resistance is defined by what it does. Now, this is something that you can do. You can define something by what it does. All right? Just remember this. You can define it by what it does. Resistance is defined by, well, two main characteristics or two main effects. It limits the amount, not the speed, the amount of current that flows. And the second thing it does is it produces heat. Well, it causes heat to be produced. as current flows. These are the two main effects of resistance. So it limits, that's the first thing it does, and it causes heat to be produced. So we have three quantities. We have current, we have voltage, we have resistance. These three are related to each other by something called Ohm's law, OHM'(S), LAW. Now, Ohm's law says two things. Not one thing, two things. The first thing Ohm said was that current is proportional to voltage. In other words, current depends on voltage. The more voltage you have, the higher the current that can flow. The second thing Ohm said was that current is inversely proportional to resistance, meaning the more resistance you have, the less current you have. That's what it means. These two statements are combined into our good old equation V is equal to I times R. And this is the equation of Ohm's law. Now, any device, before I go to any device, I should say there is a condition for Ohm's law. The condition under which Ohm's law actually works is at constant temperature. Temperature can affect the amount of current that flows in the circuit, and as a result of which, you can only say Ohm's law applies at a fixed and constant temperature. Now, if we gathered the values of current that flow through certain devices or components, electrical components, at let me start over. If we gather the values of current that flow through certain components at certain voltages, and we put them in a little table where we have current and voltage, you basically get a pair of coordinate values that you can plot. If you plot several pairs of these points, you can get a graph. This graph is called an IV characteristic. Now, there are some IV characteristics that you need to be aware of. The first is an ohmic conductor, OHMIC conductor. Something that thoroughly, fully, totally obeys Ohm's law. It would be a straight line graph starting at the origin. The next thing is a filament lamp. A filament lamp is the kind of bulb that produces that yellowish light. It has a metal element that gets heated and produces an orangish yellowish glow. That is a filament lamp. Filament lamp. The next is the semiconductor diode. And this is a little fairly odd graph. Now again, just like with electric fields, these graphs are these are sketches rather, given or done to show the shape or the general characteristics of something. These are not plots. They don't need to pass through specific points except the origin. That's it. So this is a semiconductor diode. And finally, we have I think it's copper sulfate solution, and this also is a straight line through the origin but extending over here as well. This, one second, it's copper sulfate solution, copper sulfate solution. And these are the 4 IV characteristics the syllabus says you must know. Now, I am sure, well, I shouldn't say I'm sure. we have to look at electrical power. Power, power, power. There was a man that used to sell coke up on Regent Street. I would never forget him, Uncle Powers. Uncle Powers was a cool dude. Real cool dude. Every time I say the word power, I remember Uncle Powers. The man spelled his name P-O-W-A-Z. Was hilarious talking to Uncle Powers. Man was a good, he was good people. Anyways, enough of me and my strange stories. So, power, P-O-W-E-R. Electrical power is found using this. P is equal to IV. But V is equal to IR. If we substitute IR for V, what we get is a new equation. This new equation is P is equal to I squared R. But I is equal to V over R. If we substitute this in here for I, we get a new equation altogether, another equation. And this is P is equal to V squared over R. So these three equations are the equations used to calculate electrical power. Of course, there still is the ever trusty, always faithful, power is equal to energy over time, which we used in our what is it? Yes, our methods of finding specific heat capacity, the electrical method. This does apply as well, but it's P is equal to IV, P is equal to I squared R, P is equal to V squared over R. Those are the three more commonly or appropriately used equations of power when it comes to electrical circuits and components. Now, the next thing we have to move on to, I do believe, is electrical circuits. We have to look at series, parallel, and a combination of the two. And then we have to look at some electronics, some logic gates, some magnetism, and we will be finished. I estimate I'll need another 3 episodes, or 3 videos rather, before I complete everything. And that would be it. They will be uploaded as soon as I'm finished with them. Anyways, as always, do share, like, subscribe, comment, dislike if you aren't pleased with the video. But once again, thank you very much for your support, and I will see you in the next one.